Look up at the night sky, and what do you see? A vast, swirling canvas of chaos, exploding stars, colliding galaxies, and nebulae that twist like cosmic storms. It's easy to assume the universe is a place of pure randomness, where disorder rules supreme. But what if I told you that hidden within this apparent madness are patterns so precise, so breathtakingly symmetrical, they seem to whisper a secret about the cosmos? These aren't just happy accidents, they're clues to a deeper order, a hidden harmony woven into the fabric of space itself. Today, we're embarking on a journey to uncover 29 of these unexpected symmetries, each one a stunning defiance of chaos, each one revealing how the universe balances its wildest forces with an elegance that's almost poetic. Think about the last time you saw a spiral galaxy, its arms curling outward in perfect curves, as if painted by an artist's careful hand, or the way certain nebulae mirror themselves, their glowing gases folding into shapes that feel strangely familiar. These aren't just pretty pictures, they're evidence of something profound. Symmetry is the universe's silent language, a code embedded in everything from the smallest quantum fluctuations to the grandest structures in the cosmos. And the most astonishing part, the more we look, the more we realize that what we once called chaos might actually be a dance where every step, every spin, follows a rhythm we're only beginning to understand. So why does this matter? Because these symmetries aren't just cosmic eye candy, they're keys to unlocking the universe's deepest mysteries. They challenge our assumptions about randomness, beauty, and even the nature of reality itself. What if the chaos we see is just the surface of something far more intricate? Over the course of this video, we'll explore 29 of these mesmerizing phenomena, from the way black holes align to the eerie mirroring of distant galaxy clusters. By the end, you'll never look at the night sky the same way again, ready to peer into the cosmos and discover the hidden order within the storm. Let's begin. Take a moment to picture a spiral galaxy, those vast, spinning islands of stars with arms that stretch outward like cosmic whirlpools. What's fascinating isn't just their beauty, but the precision behind it. These spirals aren't random swirls. They follow a mathematical pattern so exact, it's as if the universe sketched them with a compass. The secret lies in something called logarithmic spirals, where each curve grows wider at a constant rate, creating that hypnotic, balanced shape we see in galaxies like the Milky Way or the stunning Pinwheel Galaxy. But how does something so orderly emerge from the chaos of space? Scientists point to density, waves, ripples of compressed gas and stars that move through galaxies like traffic jams in a cosmic highway. As these waves pass through, they trigger star formation, lighting up the spiral arms. Gravity plays its part too, pulling matter into those elegant curves. Yet, even with these explanations, there's an air of mystery. Why do so many galaxies settle into this symmetrical form? It's as if the universe has a preference for spirals, a hidden rulebook that favors harmony over disorder. And here's where it gets even more intriguing. These spirals aren't just pretty patterns, they're evidence of a deeper cosmic choreography. The same mathematical principles that shape seashells and hurricanes also sculpt galaxies, hinting at universal laws that transcend scale. Whether it's the curl of a fern or the spin of a galaxy billions of light years wide, symmetry seems to be written into the fabric of reality itself. So the next time you gaze at a spiral galaxy, remember, you're not just looking at a random swirl of stars, you're witnessing a dance, one that's been playing out across the cosmos for billions of years, governed by rhythms we're only beginning to decode. Now, let's turn our gaze to one of the most striking examples of cosmic symmetry, the breathtaking bilateral balance seen in nebulae like the Butterfly Nebula. Stretching its delicate wings across the void, this celestial structure appears almost perfectly mirrored, as if an invisible line runs down its center, reflecting one half onto the other. At first glance, it's hard to believe such precision could emerge from the violent death throes of a star. Yet, this symmetry isn't an illusion, it's a cosmic signature, a clue to the hidden forces shaping the universe's most dramatic transformations. When a star reaches the end of its life, it doesn't fade quietly. Instead, it often erupts, shedding its outer layers in powerful outflows. But here's the mystery: these ejections don't spray outward in random directions. Instead, they frequently shoot out in opposing jets, creating a near-perfect mirrored effect. Imagine squeezing a water balloon tightly at its middle. The escaping streams burst out symmetrically. In a similar way, the dying star's material is funneled along two precise paths, sculpting nebulae that look like they were designed by an artist's hand. So what controls this astonishing balance? The answer lies in the star's final moments. As it collapses, its rotation speeds up, and its magnetic fields grow incredibly strong. These forces act like cosmic sculptors, channeling the ejected material into twin jets. Think of it like a spinning top. As it whirls faster, its motion becomes more stable, more predictable. The star's magnetic fields then act like invisible guides, ensuring the outflow stays symmetrical. Even in chaos, the universe finds equilibrium, but there's a deeper wonder here. This symmetry isn't just a fleeting phenomenon. It's a testament to universal laws that shape everything from the smallest atoms to the largest nebulae. The same principles that create the Butterfly Nebula's wings might also govern the formation of planets, the orbits of stars, even the structure of galaxies. It's as if the cosmos has a blueprint for balance, a set of rules that ensure even its most violent events unfold with an underlying order. Next time you see an image of a symmetrical nebula, remember, you're not just looking at a pretty space picture. You're witnessing the universe's hidden harmony, a reminder that even in the most turbulent corners of existence, there's a quiet, elegant logic at work. And the more we uncover these patterns, the closer we get to understanding the grand design behind it all. Saturn's North Pole holds a secret that seems ripped straight from the pages of a geometric puzzle, a colossal hexagon stretching wider than Earth itself, etched into the planet's atmosphere like a cosmic fingerprint. This isn't just any storm. It's a six-sided masterpiece, a jet stream whirling at speeds over 200 miles per hour, yet maintaining razor-sharp edges that defy everything we know about fluid dynamics. Picture a spinning top, but instead of wobbling into chaos, it locks into a perfect polygon, its sides unwavering even as winds rage within. It's as if Saturn decided to flaunt the universe's love of symmetry in the most dramatic way possible. What makes this hexagon so baffling isn't just its shape, but its endurance. First spotted by Voyager in the 1980s, it's outlasted every earthly weather pattern, persisting through decades of Saturn's seasons. On Earth, storms dissolve or collide, their energy dissipating into randomness. But Saturn's hexagon, it's a monument to stability, a structure that refuses to succumb to the chaos around it. Scientists suspect planetary rotation plays a starring role. The Coriolis effect, the same force that shapes Earth's hurricanes, might here sculpt the storm's edges into geometric precision. Yet, even with advanced simulations, no model fully explains how this hexagon stays so crisp, so unchanging, while the atmosphere churns violently beneath it. Dive deeper and the mystery only grows. Atmospheric waves rippling through Saturn's gaseous layers could act like invisible sculptors, reinforcing the hexagon's shape. Think of it as dropping a pebble into a pond, but instead of circular ripples, the waves somehow lock into a six-sided pattern. And then there's the question of scale. Similar shapes appear in lab experiments with spinning fluids, but those tiny vortices vanish in seconds. Saturn's hexagon, by contrast, operates on a planetary stage, its symmetry writ large across thousands of miles. It's a reminder that the laws of physics don't just apply to Petri dishes, they scale up to celestial proportions, sometimes in ways we never anticipated. But perhaps the most tantalizing thought is this: the hexagon isn't just a curiosity, it's a clue. Across the cosmos, from the spiral arms of galaxies to the double jets of dying stars, symmetry emerges again and again, as if the universe is whispering a pattern we're only beginning to hear. Saturn's storm is more than a weather anomaly. It's a testament to the hidden order lurking within even the most turbulent systems. So the next time you see a snowflake's delicate branches or the honeycomb's perfect cells, remember, they're part of the same cosmic language, one that Saturn speaks in bold, geometric strokes. There's a number sequence so elegant, so universal, that it shows up everywhere, from the curl of a seashell to the branching of trees, even in the way your fingers grow. It's called the Fibonacci Sequence, where each number is the sum of the two before it. 0, 1, 1, 2, 3, 5, 8, and so on, stretching infinitely outward. But here's the astonishing part: this isn't just a quirk of earthly biology. The Fibonacci sequence is woven into the very fabric of the cosmos, from the arms of spiral galaxies to the silent dance of planets around their stars. Consider the humble sunflower. Its seeds spiral outward in patterns that precisely match Fibonacci numbers, packing efficiently to maximize space. Now, look at a galaxy like Messier 74, its arms unfurling in that same hypnotic spiral. The resemblance isn't coincidence. Both follow what's known as the golden ratio, a mathematical proportion derived from the Fibonacci sequence, where each turn or layer grows by a factor of roughly 1.618. This ratio creates a shape that's not just beautiful but functionally perfect. In galaxies, it allows for stable, energy-efficient orbits. In sunflowers, it ensures every seed gets room to grow. The universe, it seems, has a favorite blueprint, but why? Why would a pattern discovered by a 13th century mathematician govern the structure of something as vast as a galaxy? The answer lies in the laws of physics themselves. Nature is a master of optimization, always seeking the path of least resistance. The golden ratio represents the most efficient way to pack matter, distribute energy, or maintain balance in a spinning system. When a galaxy forms, gravity pulls matter into a disk, but rotation twists it. The result: a spiral where stars and gas follow Fibonacci-like paths, minimizing collisions and maximizing stability. Even the spacing of planets in our solar system hints at this pattern, with orbital resonances often aligning with ratios close to Fibonacci numbers. The deeper you dig, the more surreal it becomes. Black holes, those cosmic vacuum cleaners, may also play by these rules. Some theories suggest the jets they emit could spiral in golden ratio proportions, channeling energy in eerily efficient ways. And then there's the large-scale structure of the universe: filaments of galaxies stretching across the void in web-like patterns that, when analyzed, echo Fibonacci-like growth. It's as if the universe is solving a puzzle, one where the golden ratio is the key to harmony amid chaos. So what does this all mean? Perhaps the Fibonacci sequence isn't just a human discovery, but a universal truth, a silent law written into the cosmos long before we existed to name it. From the smallest seed to the grandest galaxy, the universe repeats this pattern like a mantra, a reminder that even in the infinite vastness of space, there's an order, a rhythm, a beauty that connects everything. And every time we find it, in a flower, a storm, or a star, we're glimpsing a deeper truth, that the chaos of the cosmos might just be a symphony playing a tune we're only beginning to hear. Imagine a material so strange, it defied every rule scientists thought they knew about crystals. For centuries, we believed that all crystals had to follow one unbreakable law. Their atoms must arrange in perfectly repeating patterns, like tiles on a bathroom floor. That was the rule. Then, in 2009, a meteorite crashed into our understanding literally. Inside a space rock found in Russia, researchers uncovered something revolutionary: quasi-crystals. These weren't just unusual crystals, they were cosmic rebels with atoms arranged in ordered yet never repeating patterns, boasting a symmetry once deemed impossible in nature: five-fold symmetry, like a starfish stretched across the atomic scale. What makes this discovery so mind-bending? Picture trying to tile your floor with pentagons. No matter how you arrange them, gaps will always appear. That's why, for decades, scientists insisted five-fold symmetry couldn't exist in crystalline structures. Yet here were quasi-crystals, laughing in the face of that assumption, their atoms locked into a mesmerizing dance of fives, tens, and even 12 symmetries that shouldn't work, but somehow do. And they didn't come from a lab. They were forged in the violent chaos of space, inside a meteorite that had wandered the solar system for billions of years. Now here's where it gets even wilder. These quasi-crystals didn't form under ordinary conditions. They're thought to be the children of cosmic collisions, moments when asteroids slammed together with such force, such heat and pressure, that the rules of chemistry twisted into something new. It's as if the universe, when pushed to its limits, starts playing by a different playbook, and that raises a tantalizing question. If quasi-crystals can form naturally in the chaos of space, what other, impossible materials might be lurking out there, waiting to rewrite our textbooks? But the implications go deeper than just atomic oddities. Quasi-crystals could be time capsules, preserving clues about the early solar system's most violent moments. Their unique structure makes them incredibly hard, resistant to heat, and eerily efficient at conducting energy properties that might explain why they survived their interstellar journey. Some scientists even speculate that quasi-crystals could be more common in the cosmos than we realize, hiding in plain sight within other meteorites or distant planetary bodies. Think about that for a second. We've spent centuries studying crystals, convinced we understood their rules, only for the cosmos to hand us a paradox, a material that shouldn't exist, yet clearly does. It's a humbling reminder that the universe's creativity far outstrips our imagination. From the perfect spirals of galaxies to the atomic rebellion of quasi-crystals, symmetry keeps revealing itself as the universe's secret language, one we're only starting to decipher. And every time we think we've figured it all out, space tosses us another puzzle, another whisper of the order hidden within the chaos. In the swirling chaos around a black hole, where gravity twists space-time into knots and matter spirals inward at nearly the speed of light, you'd expect nothing but disorder. Yet in 2019, humanity glimpsed something astonishing, a shadow so perfectly round it might have been drawn with celestial compass. The Event Horizon Telescope's groundbreaking image of the supermassive black hole at the heart of Galaxy Messier 87 revealed an eerie halo of light encircling a dark void, its edges so symmetrical they seemed to defy the violence of the environment. Here, in the most extreme gravitational arena in the universe, symmetry reigned supreme. This circular perfection isn't just a visual marvel, it's a cosmic confirmation of Einstein's century-old equations. General relativity predicts that a black hole's immense gravity bends light so severely, it wraps around the event horizon like a taut ribbon, creating a shadow roughly 2.6 times wider than the hole itself. What's staggering is how uniform this shadow appears despite the chaos surrounding it. Matter near a black hole doesn't fall in neatly. It's torn into superheated plasma, ejected in turbulent jets, and whipped into frenzied orbits. Yet when all that chaos is filtered through the lens of gravity, the result is a shape of serene simplicity, a circle. But why this symmetry? The answer lies in the black hole's spin. While most black holes rotate, some at nearly the speed of light, their shadows remain circular because gravity distorts light equally in all directions, like a funhouse mirror with perfect precision. Even if the black hole is slightly squashed by its spin, relativistic effects compensate, preserving that flawless silhouette. It's as if the universe has a failsafe, a way of maintaining order even in the most extreme conditions. Then there's the deeper mystery, what this symmetry tells us about spacetime itself. The shadow's perfection suggests that, on some fundamental level, gravity behaves like a cosmic sculptor, smoothing out irregularities until only harmony remains. Some theorists even speculate that black hole shadows might encode secrets about higher dimensions or quantum gravity, clues to how Einstein's relativity and quantum mechanics might finally reconcile. After all, if symmetry persists where physics breaks down, what does that say about the fabric of reality? Think about the irony here. Black holes are the ultimate endpoints of entropy, places where matter and energy are crushed into oblivion. Yet their shadows, their very fingerprints, are models of geometric purity. It's a paradox that challenges our understanding of chaos and order, suggesting that symmetry isn't just a feature of the universe's calm corners, but also its most violent storms. So the next time you see that iconic image of the black hole's shadow, remember, you're not just looking at a dark circle. You're seeing the universe's quiet insistence that, even in the heart of darkness, there's a pattern, a rhythm waiting to be understood. Down at the quantum level, where particles flicker in and out of existence like sparks in the void, space-time itself seems to tremble. Scientists call this bizarre, ever-shifting landscape quantum foam, a seething sea of tiny bubbles where the fabric of reality churns unpredictably. It's chaos in its purest form, a realm where certainty dissolves and even the concept of here and now loses meaning. Yet, buried within this turbulence, something extraordinary emerges. Symmetries so delicate, so precise, they hint at a hidden architecture beneath the froth. Imagine zooming in on a fractal, a shape that repeats itself infinitely. No matter how closely you look, the jagged edge of a snowflake, the branching veins of a leaf, the winding path of a river. Now picture spacetime behaving the same way. Some theories propose that the quantum foam isn't just random noise. It's a fractal tapestry with patterns echoing across scales from the subatomic to the cosmic. Tiny fluctuations in the foam might ripple outward, shaping the large-scale structure of galaxies, while galactic symmetries could mirror the geometry of the quantum realm. It's as if the universe is whispering the same secret in every language, from the tiniest whisper of a particle to the thunderous roar of a supercluster. But how could such a connection exist? The answer might lie in the very nature of energy and gravity. At the quantum level, particles exchange energy in discrete packets, creating a frothy, dynamic spacetime. Zoom out, and gravity, Einstein's cosmic sculptor, takes over, weaving those microscopic fluctuations into the fabric of the universe. The same mathematical principles that govern quantum entanglement might also dictate the distribution of galaxies, creating a cosmic hall of mirrors where the small and the vast reflect one another. Think about the implications. If the universe truly operates like a fractal, then every spiral galaxy, every nebula, every black hole's shadow could be a scaled-up version of processes occurring in the quantum foam. The Fibonacci sequence in a sunflower seed, the logarithmic spirals of hurricanes, the hexagonal storm on Saturn, all might be surface ripples of a deeper, self-similar reality. Even the cosmic microwave background, the afterglow of the Big Bang, shows patterns that resemble the clustering of particles in a quantum field. Coincidence? Or evidence of a grand, repeating design? This idea doesn't just challenge our understanding of scale, it blurs the line between chaos and order. In a fractal universe, randomness isn't truly random, it's a cascade of symmetries, each layer building on the last. The same forces that twist spacetime into knots around a black hole might also stir the quantum foam into fleeting, beautiful patterns. And if that's true, then every time we gaze at the night sky, we're not just seeing stars, we're glimpsing the universe's blueprint, a code written in the language of repeating shapes, echoing from the smallest whisper of existence to the grandest structures in the cosmos. Picture the universe in its infancy, a seething, scorching plasma so dense, so uniform that light couldn't even travel freely through it. Then, in an instant, everything changed. That plasma cooled, light broke free, and the cosmos became transparent for the first time. The glow from that moment still lingers today, a faint whisper of microwaves bathing the entire universe, the cosmic microwave background. What's astonishing isn't just its existence, but its near-perfect smoothness. No matter where you point a telescope, the temperature of this ancient light varies by less than 1 part in 100,000. Our uniformity so precise, it's like the universe took a deep breath and exhaled equilibrium. But here's the puzzle. If the early cosmos was this balanced, how did we end up with a universe full of galaxies, stars, and cosmic voids? The answer lies in the tiniest of imperfections. Those minuscule fluctuations in the CMB, smaller than the variations in a billiard ball's surface, were the seeds of everything we see today. Gravity amplified them over billions of years, pulling matter into denser regions while leaving others empty. The result, the cosmic web we inhabit, with its glittering galaxies and vast, dark stretches. It's as if the universe started with a blank canvas, then added just the faintest brushstrokes of unevenness enough to create all the complexity we know. So how did it stay so smooth to begin with? Enter inflation, one of the most daring ideas in cosmology. In the first fraction of a second after the Big Bang, the universe may have undergone an exponential growth spurt, expanding faster than the speed of light itself. This runaway stretching would have ironed out any wrinkles, smoothing the cosmos like a hot plate flattening dough. Any irregularities that existed before inflation would have been stretched so thin they'd vanish from view. What remained was a universe so uniform, its echo, the CMB, still bears that signature of balance today. Yet, inflation didn't erase all variation. Quantum fluctuations, those tiny jitters in the fabric of reality, were stretched along with everything else, imprinting themselves as the faint temperature differences we now detect. These became the blueprints for galaxies. Think of it like blowing up a balloon with tiny dots on its surface. Inflate it enough, and the dots spread apart, but their pattern remains. The universe did the same, magnifying quantum randomness into cosmic structure. But the CMB's symmetry isn't just a relic, it's a time machine. By mapping its subtle variations, scientists can peer back to the universe's first moments, testing theories like inflation, and even probing the nature of dark matter and dark energy. The Planck satellite's ultra-precise measurements reveal patterns that hint at physics beyond our current understanding, like shadows of hidden dimensions or exotic particles. It's as if the CMB is a cryptogram, its isotropic glow masking layers of cosmic secrets waiting to be decoded. And then there's the haunting beauty of it all. That microwave static on old television sets, 1% of it comes from this primordial light, the afterglow of creation itself. Every time you see that snow, you're glimpsing the universe's earliest symmetry, a whisper from 13.8 billion years ago. The CMB reminds us that beneath the chaos of galaxies colliding and stars exploding, there's an underlying order, a balance so profound, it shaped everything from the largest supercluster to the smallest atom. And perhaps that's the most breathtaking symmetry of all, the way the universe's first moments still echo in the silence between the stars. Gravity, for all its crushing power, has a softer side, a talent for coaxing celestial bodies into rhythmic dances so precise they mimic the ticking of a cosmic metronome. Take Jupiter's inner moons, Io, Europa, and Ganymede. For every single orbit Ganymede completes around the gas giant, Europa circles exactly twice, and tiny volcanic Io races around 4 times. This 1-2-4 rhythm isn't random. It's a gravitational waltz called an orbital resonance, where the pull of neighboring worlds locks them into synchrony. Amid the swirling chaos of Jupiter's immense gravity, these moons move like gears in a celestial clockwork, their paths intertwined by invisible threads of physics. What's astonishing isn't just the precision of this dance, but how common it is across the cosmos. From the way Neptune and Pluto avoid collisions orbiting in a 2-3 resonance to the intricate choreography of Saturn's rings, where tiny moons shepherd particles into razor-sharp gaps, resonances sculpt planetary systems into stability. They act like cosmic traffic cops, ensuring orbits don't degenerate into chaos. Without them, moons might spiral into their planets or fling each other into the void. Instead, resonances create pockets of order where gravitational nudges balance perfectly over time, like a pendulum finding its natural rhythm. But how does this work? Picture pushing a child on a swing. If you time your pushes just right, syncing with the swing's natural motion, each push adds energy, making the child soar higher. Miss the timing, though, and the energy scatters, disrupting the rhythm. Orbital resonances operate the same way. When 2 bodies' orbits align in simple ratios, their gravitational interactions reinforce rather than disrupt. Europa's gentle tugs on Io, for example, add energy at just the right moments, keeping their orbits locked in sync. The result, a self-correcting system where chaos is kept at bay by mathematics itself. The consequences ripple far beyond orbital mechanics. Resonances shape climates, tides, even the potential for life. Europa's resonance with Io generates tidal heating, flexing its icy shell enough to maintain a subsurface ocean, a hidden sea that might harbor alien organisms. Meanwhile, in distant exoplanet systems, resonances could funnel comets toward inner planets, delivering water or triggering extinctions. These patterns aren't just curiosities, they're architects of habitability, quietly orchestrating the conditions that make worlds livable or lethal. Yet, the deepest wonder lies in their universality. From the delicate dance of asteroid pairs to the grand resonance chains of TRAPPIST-17 Earth-sized planets, these harmonies emerge again and again. It's as if the universe, when left to its own devices, defaults to rhythm over randomness. Even Saturn's dazzling rings, often seen as emblems of chaos, are sculpted by resonances, their gaps and waves frozen records of gravitational symphonies. So the next time you look at the moon, remember, its steady orbit around Earth is no accident. It's part of a vast, silent music, a cosmic tendency to find order amid the storm. And somewhere, in the darkness between stars, other worlds are dancing to the same timeless tune, their motions locked into patterns that whisper of a universe far more harmonious than we ever imagined. The whirlpool galaxy spins gracefully through the void, its arms unfurling in a curve so mathematically perfect it could have been sketched by a cosmic architect. This isn't just any spiral, it's a golden spiral, growing outward at a rate of 1.618 with each full rotation, the exact proportion celebrated in art, architecture, and nature for millennia. But why would a galaxy billions of light years wide adhere to the same geometric rule as a nautilus shell or a sunflower seeds? The answer lies in the silent mathematics of efficiency, where the universe defaults to patterns that conserve energy and optimize growth. At first glance, the golden spiral seems like an aesthetic accident, a beautiful coincidence, but peer closer and its brilliance becomes clear. In galaxies like the whirlpool, this logarithmic shape allows for an elegant distribution of matter. Stars and gas clouds along the arms follow paths where gravitational forces balance perfectly with centrifugal motion, creating stable orbits that minimize collisions and chaos. It's nature's way of packing the most material into the least space without wasteful overlaps or gaps. Think of it like a cosmic highway system, where the golden ratio dictates the spacing of on-ramps to prevent traffic jams in the void. What's even more striking is how this spiral fosters star formation. As density waves ripple through a galaxy's disk, they compress gas clouds along the golden curve's expanding arcs. These regions become stellar nurseries where the spiral's precise geometry ensures new stars ignite at optimal intervals, not too crowded to trigger destructive supernova, not too sparse to stall galactic evolution. The spiral isn't just pretty, it's a functional blueprint, a self-regulating system that sustains creation over billions of years. But the real magic lies in the numbers. The golden ratio emerges from the Fibonacci sequence, where each term is the sum of the two before it. This sequence appears everywhere, from the branching of trees to the arrangement of leaves, because it represents the most efficient way to grow without overlap. In galaxies, the same principle applies. As a spiral arm stretches outward, each segment builds upon the last, maximizing space while maintaining structural integrity. The universe, it seems, recycles its best designs across scales, from microscopic algae to megastructures light years across. The implications ripple beyond mere geometry. If the golden spiral governs galactic growth, it suggests a deeper connection between mathematics and physics, a universe where abstract numbers shape tangible reality. Some theorists even propose that dark matter, the invisible scaffolding of galaxies, might distribute itself according to these ratios, its gravitational influence subtly reinforcing the spiral's perfection. Others see the golden ratio as a fingerprint of universal constants, a hint that the laws of physics themselves might be rooted in mathematical harmony. So when you gaze at images of the whirlpool galaxy, remember, you're not just seeing a swirl of stars, you're witnessing a cosmic equation in motion, a testament to the universe's quiet preference for balance and beauty. From the curl of a fern to the whirl of a galaxy, the same silent rules apply, proving that even in the vastness of space, there's an elegance as intimate as it is infinite. Time crystals sound like something ripped from a science fiction novel, matter that repeats not just in space but in time itself, ticking like a clock without any energy input. Yet in 2016, physicists turned this wild idea into reality, synthesizing the first time crystals in labs using chains of ytterbium atoms. These bizarre structures don't settle into equilibrium like normal matter. Instead, they oscillate between states indefinitely, their atomic patterns cycling with perfect regularity, as if the universe handed them a metronome. What's even stranger, they achieve this without violating the laws of thermodynamics, dancing eternally in a realm between quantum curiosity and cosmic inevitability. How does matter behave this way? Normally, if you nudge a system like a pendulum, it eventually stops as energy dissipates. Time crystals flip this expectation. When gently pulsed with a laser, their atomic arrangement doesn't wind down. Instead, it locks into a rhythm, repeating at a fraction of the laser's frequency. Imagine pushing a swing every 10 seconds, only for it to complete a full arc every 20, a defiance of intuition that reveals a new phase of matter, one where time itself becomes a canvas for symmetry. This isn't just a laboratory party trick, it's a window into physics' deepest mysteries. The implications ripple far beyond Earth. Theorists speculate that time crystals might form naturally in the most extreme corners of the cosmos, perhaps within neutron stars, where crushing gravity and quantum forces collide. Picture a star's core denser than an atomic nucleus, spinning hundreds of times per second. In that maelstrom, particles could arrange into temporal patterns, their oscillations frozen in the star's absurdly strong magnetic fields. Even black holes, those ultimate disruptors of time, might host time crystal-like behavior at their boundaries where space-time twists into knots. If so, these exotic structures could be hiding in plain sight, their rhythmic pulses camouflaged as mundane stellar activity. What's most mind-bending is how time crystals bridge quantum mechanics and cosmology. They exist because of many-body localization, a phenomenon where quantum systems resist thermal equilibrium, a property that might also explain how information escapes black holes. Some researchers even suggest time crystals could model the early universe's behavior, offering clues about how time itself emerged from the Big Bang's chaos. It's as if these tiny, man-made structures are echoing the universe's own heartbeat, a faint but perceptible rhythm beneath the noise. Yet the real revolution lies in what time crystals imply about symmetry. We're used to spatial symmetry, snowflakes, galaxies, crystals, but temporal symmetry, that's uncharted territory. If matter can spontaneously develop order in time, not just space, our understanding of entropy, evolution, even the arrow of time might need rewriting. Perhaps the cosmos doesn't just favor symmetry, it demands it, weaving patterns not only across the void but through the very fabric of existence. And if time crystals do lurk in neutron stars or black holes, they're not just curiosities, they're cosmic signatures, reminding us that the universe's order runs deeper, stranger, and more beautifully than we ever dreamed. Neutrinos are the universe's ultimate shape-shifters, particles so ghostly, they pass through entire planets like they're not even there. Yet, as they race through space at nearly the speed of light, they undergo a mesmerizing metamorphosis, flipping between three distinct flavors: electron, muon, and tau. This chameleon-like behavior, known as neutrino oscillation, isn't random. It follows a rhythm so precise, so mathematically elegant, it's as if the particles are dancing to a cosmic symphony written in the language of symmetry. What makes these oscillations so extraordinary is their predictability. Unlike the chaotic decay of other particles, neutrinos switch identities with clockwork regularity, their transformations governed by probabilities that mirror the clean, repeating patterns of a pendulum swing. Picture a deck of cards being shuffled, but instead of randomness, every shuffle follows an exact sequence, aces always turning into kings, kings into queens, and back again. That's the level of order we're talking about. Scientists describe this behavior using a mathematical framework called the Piermann matrix, which maps out the probabilities of each transition with near-perfect accuracy. It's a formula so reliable, it hints at a deeper harmony woven into the fabric of reality itself. But why do neutrinos oscillate at all? The answer lies in their mass. For decades, physicists assumed these particles were weightless like photons. Then came the shocking revelation: neutrinos have tiny, non-zero masses, and it's this slight heaviness that drives their transformations. As they travel, their quantum states evolve, causing their flavors to mix and shift in a process akin to waves interfering on a pond. The symmetry emerges from how these quantum waves overlap constructive interference, amplifying certain flavors while canceling others, all according to those elegant probabilities. Here's where it gets even more intriguing. Neutrino oscillations might hold the key to one of the universe's greatest mysteries, why we exist at all. During the Big Bang, matter and antimatter should have annihilated each other in a burst of pure energy, leaving behind an empty cosmos, yet somehow matter won out. Neutrinos, with their subtle asymmetries in oscillation behavior between particles and antiparticles, could be the culprits behind this imbalance. If they interact even slightly differently with matter versus antimatter, a phenomenon called charge parity violation, it could explain how the scales tipped in favor of stars, planets, and us. Experiments like Japan's T2K and the upcoming Deep Underground Neutrino experiment are racing to measure these asymmetries with unprecedented precision. By firing beams of neutrinos through hundreds of miles of Earth and tracking their flavor changes, they're piecing together a puzzle that spans the entire universe. Every oscillation, every flip from muon to electron neutrino, carries whispers from the early cosmos, clues about how symmetry broke in just the right way to make life possible. So the next time you gaze at the night sky, remember, those invisible, shape-shifting particles streaming through your body aren't just cosmic ghosts. They're time travelers carrying secrets from the universe's first moments, and their rhythmic, symmetrical dance might just be the reason you're here to witness it. Stretching across the void like luminous threads in a spider's web, vast filaments of glowing plasma connect galaxies in a cosmic network so immense it defies comprehension. These are no ordinary structures, they're highways of electrified gas, shaped and steered by invisible forces called Birkeland currents, named after Norwegian scientist Christian Birkeland, who first proposed their existence over a century ago. These currents are the universe's hidden wiring, carrying energy across millions of light years with a precision that rivals the most intricate circuitry. And what's most astonishing isn't just their scale, but their symmetry. These filaments branch, twist, and intersect in patterns so harmonious, they seem to follow a grand electromagnetic blueprint. For decades, astronomers assumed gravity alone sculpted the universe's large-scale structure. But Birkeland currents reveal a startling truth. Electromagnetism may be the silent architect behind the cosmos' most breathtaking designs. Picture a lightning bolt, frozen in time and stretched to galactic proportions. That's the essence of these currents. They form when charged particles spiral along magnetic field lines, creating twisting plasma ropes that can power star formation, ignite quasars, and even govern the motion of entire galaxy clusters. The evidence is etched across the sky. In galaxy clusters like Perseus, X-ray telescopes have captured vast loops of plasma, their shapes too orderly to be gravity's handiwork alone. Meanwhile, radio telescopes reveal filamentary structures linking galaxies like beads on a string, their alignment too precise for chance. The symmetry of these currents isn't just visual, it's functional. Like the veins in a leaf or the nerves in a body, they distribute energy efficiently, balancing the cosmos' chaotic forces. Take the famous cosmic web, the filamentary scaffolding that connects galaxies across the universe. While gravity pulls matter into these threads, Birkeland currents likely stabilize them, preventing collapse or fragmentation. It's a partnership of forces. Gravity provides the rough draft, electromagnetism refines it into lasting structure. And the results are everywhere. In the Sloan Great Wall, one of the largest known cosmic filaments, Galaxies aren't scattered randomly, they're strung along plasma currents like pearls on a necklace, their spacing eerily uniform. But how do these currents form on such mind-boggling scales? The answer may lie in the universe's infancy. During the Big Bang, fluctuations in the primordial plasma could have generated magnetic fields, which then stretched and amplified as the cosmos expanded. Over billions of years, these fields organized the electrified gas into the filaments we see today, their symmetry preserved by the relentless discipline of electromagnetic physics. It's as if the universe spun a web of invisible silk, then charged it with starlight. Now, here's the twist. These currents might not just connect galaxies, they could control them. Some theorists suggest Birkeland currents funnel matter into galactic centers, feeding supermassive black holes and sparking quasars. Others propose they regulate star formation, like cosmic dimmer switches, by channeling or restricting the flow of ionized gas. Even dark matter, that elusive cosmic glue, might interact with these currents in ways we're only beginning to guess. If true, it would mean electromagnetism isn't just a background player in cosmic evolution, it's a director shaping the universe's story from behind the scenes. So the next time you see an image of the cosmic web, remember, those glowing strands aren't just pretty patterns, they're evidence of a deeper order, a symmetry woven into the universe's very fabric. And as we trace these filaments back to their origins, we're not just mapping the cosmos, we're reading its hidden blueprints, one electrified thread at a time. Some of the boldest ideas in cosmology don't come from telescopes or supercomputers, they emerge from the simple observation of a shape. Take the tetrahedron, a four-faced pyramid, one of the most fundamental forms in geometry. Now imagine that same shape scaled up to cosmic proportions, with galaxy clusters marking its corners and vast voids stretching between its edges. This is the essence of the tetrahedral universe hypothesis, a theory so audacious it reimagines the cosmos as a geometric masterpiece rather than a product of random chance. At first glance, the idea seems improbable. After all, we're used to thinking of the universe as a bubbling froth of galaxies, uneven and chaotic, but look closer and patterns emerge. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing a surprising tendency for superclusters to align in ways that hint at larger, unseen structures. Some theorists argue these alignments aren't random, they're vertices of a cosmic tetrahedron, a framework so vast we're only seeing fragments of its edges from our vantage point. Picture standing at the base of a mountain so enormous you mistake its slope for the horizon. That's the challenge of detecting a universe-sized tetrahedron. We're inside it, too small to perceive its full shape. What would such a structure imply? For starters, it would demand a radical rethink of how matter distributed itself after the Big Bang. Current models rely on quantum fluctuations, tiny ripples in the early universe that grew into today's galaxies. But a tetrahedral framework suggests those fluctuations weren't entirely random. They were channeled by some deeper geometric constraint. Perhaps space-time itself has an inherent grain, like wood, guiding the growth of cosmic structure along preferred axes. Or maybe dark matter, that invisible cosmic scaffolding, clumped in ways that favored tetrahedral symmetry. Either way, the implications would rewrite textbooks. Skeptics, of course, abound. The universe is unimaginably vast, and spotting a tetrahedron in the noise of galaxy surveys is like finding a specific grain of sand on a beach. Yet intriguing clues persist. Certain large-scale anomalies like the mysterious axis of evil, a preferred direction in the cosmic microwave background, could hint at underlying geometric order. Even the distribution of quasars, those brilliant galactic cores, shows odd alignments that some researchers link to a tetrahedral lattice. If these patterns aren't flukes, they might be shadows cast by the universe's hidden skeleton. But here's the most tantalizing thought. If the cosmos does have a tetrahedral blueprint, it wouldn't just be a curiosity, it could be a clue to deeper physics. Some string theorists propose that extra dimensions, curled up at microscopic scales, might project geometric patterns onto our observable universe. Others suggest that the tetrahedron reflects the universe's topology, its fundamental shape in higher dimensional space. Imagine blowing up a four-dimensional balloon. As it expands, its three-dimensional shadow might resemble a tetrahedron. Far-fetched, perhaps, but history shows that the universe often reserves its greatest surprises for those willing to question the obvious. So while the tetrahedral universe remains unproven, its very proposal is a victory for cosmic imagination. It reminds us that the universe's symmetries might not stop at spirals and spheres. They could extend to forms so grand, so geometrically pure, we've yet to recognize them. And if future telescopes one day confirm this wild hypothesis, it won't just reshape cosmology. It'll redefine our place in a universe that, for all its apparent chaos, might have been following a geometric script all along. Deep within the equations of particle physics lies a symmetry so profound, it could rewrite our understanding of reality itself. Supersymmetry, or SUSY, proposes that every known particle in the universe has a hidden twin, a superpartner with a subtle but crucial difference. Its spin differs by exactly half a unit. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. At first glance, this might sound like science fiction, but the math behind it is startlingly elegant, weaving together the four fundamental forces of nature into a single, symmetrical framework. Why would the universe demand such doubling? One answer lies in the glaring gaps in our current physics. The standard model, while incredibly successful, can't explain dark matter's invisible grip on galaxies or why gravity is so weak compared to other forces. SUSY elegantly fills these voids. If superpartners exist, the lightest among them could be the elusive dark matter, their feeble interactions with ordinary matter explaining why we've failed to detect it directly. Meanwhile, the symmetry's balancing act might bridge quantum mechanics and general relativity, finally revealing how gravity operates at the subatomic level. It's as if nature, faced with the chaos of particle interactions, chose harmony over discord. The beauty of SUSY isn't just theoretical. If superpartners exist, they'd leave fingerprints in high-energy collisions, tiny discrepancies in energy, or unexpected particle tracks. For decades, physicists have hunted these clues in accelerators like the Large Hadron Collider, where protons smash together at near-light speeds. So far, no definitive superpartners have appeared, but the search has refined our understanding of energy scales and symmetry breaking. Some theorists argue we've simply not reached high enough energies. Others speculate superpartners might be hidden in extra dimensions or decay too quickly to spot. The suspense is part of the allure. Every null result tightens the constraints, pushing SUSY into more nuanced territory. Beyond the physics, SUSY touches something deeper, a philosophical yearning for unity. For centuries, scientists have sought patterns that simplify the cosmos, from Newton's gravity unifying celestial and earthly motion to Maxwell's equations marrying electricity and magnetism. SUSY represents the next step in this grand tradition, a symmetry so sweeping, it could reduce the universe's complexity to a handful of equations. Even if future experiments rule it out, the pursuit has already reshaped mathematics, inspired string theory, and revealed how deeply intertwined symmetry is with reality's blueprint. So while SUSY remains unproven, its influence is undeniable. It challenges us to ask, is the universe's apparent messiness just a veil beneath which lies an order so perfect, so symmetrical, that it transcends our current imagination? Whether or not superpartners lurk in the quantum shadows, the quest to find them reminds us that the cosmos has a habit of reserving its greatest wonders for those who dare to seek balance in the chaos. Among the most dazzling structures in the realm of abstract mathematics lies a shape so complex it defies visualization, a 248-dimensional object known as the E8 Lie group. To call it intricate would be an understatement. Its symmetries form a labyrinth of geometric relationships so precise, they've been called the mother of all symmetries. Yet here's the extraordinary twist. This mathematical marvel, born from pure theory, might hold the key to unraveling the universe's deepest secrets. Some physicists propose that E8's dizzying geometry could encode every known particle and force in nature, weaving them into a single, elegant framework, a potential theory of everything. At its heart, the E8 hypothesis challenges our very understanding of reality's fabric. Imagine a cosmic tapestry where every thread, every quark, photon, and gravitational wave is a vibration of this singular geometric form. The mathematics suggests that particles we perceive as distinct could simply be different facets of E8 symmetry, like reflections of light splitting through a prism. Even forces as disparate as electromagnetism and gravity might emerge from its structure, unified at energies so high they've only existed microseconds after the Big Bang. It's as if the universe left behind a mathematical fingerprint, and E8 is the mold that shaped it. Why would a geometric object have anything to do with physics? The answer lies in the uncanny way nature mirrors mathematics. Time and again, abstract symmetries invented by mathematicians, often centuries before their practical use, turn out to describe physical phenomena with eerie accuracy. Take the electron spin, predicted by the symmetry of the Dirac equation long before it was observed, or the Higgs boson, hinted at by broken symmetries in particle physics decades before its discovery. E8 follows this tradition, but on a grander scale. Its symmetry group is so vast, it could encompass every interaction in the standard model, while leaving room for the unknown dark matter, extra dimensions, even the elusive graviton. Skeptics, of course, raise valid concerns. For one, E8's complexity makes it notoriously difficult to test. Unlike simpler symmetries that yield clear predictions, E8's sheer size means it could describe countless possible universes, not just ours. Then there's the problem of symmetry breaking, the process by which the universe's pristine symmetries fractured into the messy diversity we see today. How E8's perfect order decayed into the asymmetry of stars, planets, and people remains an open question, yet proponents argue these aren't dead ends but clues. The same way ice crystals form unique patterns as water freezes, E8's symmetry breaking might have dictated the structure of reality itself. Perhaps the most tantalizing aspect of E8 is what it implies about the cosmos. If true, it would mean the universe isn't just governed by mathematics, it is mathematics. The particles zipping through your body, the light from distant stars, even the curvature of space-time could all be shadows cast by this geometric giant. And while the theory remains speculative, its mere possibility reminds us of a profound truth. The universe's chaos might be an illusion, a veil over a deeper symmetry waiting to be uncovered. Whether E8 holds the ultimate answer or not, its exploration is a testament to humanity's quest to find order in the storm and perhaps in doing so, discover our place within it. When a massive star reaches the end of its life, it doesn't just fade away, it detonates with unimaginable force, blasting its guts across light years of space. In the aftermath, we'd expect nothing but chaos, a messy splatter of debris expanding in all directions. Yet when we point our telescopes at supernova remnants like the Crab Nebula, we're greeted by something startling, a near-perfect sphere of glowing filaments, or in some cases, elegant bipolar jets shooting from either pole like cosmic hourglasses. This isn't what randomness looks like. It's as if the universe took the violence of stellar death and sculpted it into geometric art. So how does an explosion, the very definition of disorder, produce such symmetrical wreckage? The secret lies in the star's final moments. Before going supernova, massive stars often develop layered interiors like onions, with lighter elements like hydrogen and helium floating above denser cores of carbon, oxygen, and iron. When the core collapses, it doesn't just implode randomly, it sends shockwaves racing outward through these layers with astonishing precision. Think of tossing a pebble into a perfectly still pond. The ripples spread evenly in all directions. Now replace the pebble with a collapsing stellar core and the pond with a star's interior, and you've got the recipe for a spherical supernova remnant. But what about those breathtaking bipolar remnants, the ones shaped like twin lobes or hourglasses? Here, the star's rotation and magnetic fields take center stage. As the dying star spins faster in its death throes, its magnetic fields coil into tight spirals, channeling the explosion's energy along the rotational axis like cosmic fire hoses. The result, two opposing jets of material screaming into space at nearly the speed of light, while the rest of the star's bulk expands more evenly around the equator. It's the difference between a balloon popping randomly and one squeezed tightly at the middle. The energy has to go somewhere, and in supernova, that somewhere often follows the path of least resistance dictated by physics itself. The implications ripple far beyond aesthetics. These symmetrical remnants are cosmic recycling plants, forging heavy elements in their fiery hearts before scattering them across interstellar space. The Crab Nebula's filaments, for instance, are rich in carbon, oxygen, and even gold, seeds for future planets and potentially life. Without the orderly expansion of supernova remnants, these elements might clump inefficiently or get trapped in dense pockets. Instead, symmetry ensures they disperse evenly, like fertilizer spread across galactic soil. Yet mysteries remain. Why do some supernova produce flawless spheres while others form intricate bipolar structures? The answer might lie in the star's initial masses or their binary companions. Some theorists suggest that stars with close partners are more likely to explode asymmetrically, their shapes warped by gravitational tugs from neighboring bodies. Others point to exotic physics in the collapsing core, where quantum fluctuations could tip the balance between spherical and jet-like explosions. Every new supernova we observe adds another piece to this puzzle, revealing how the universe turns chaos into order on the grandest scales. So the next time you see an image of the Crab Nebula's delicate filaments or the bipolar elegance of SN 1987A, remember, you're not just looking at a dead star. You're witnessing the universe's remarkable ability to impose balance even in its most violent acts, a reminder that destruction and creation are two sides of the same cosmic coin. And in that symmetry, we find the origins of everything from the iron in our blood to the silicon in our planet's proof that even in death, stars give birth to new possibilities. The holographic principle turns everything we think we know about reality on its head. What if the three-dimensional world we experience is just a projection, like a movie playing on the surface of an invisible cosmic screen? This mind-bending idea didn't come from science fiction. It emerged from the study of black holes, where physicists stumbled upon a paradox that threatened to unravel our understanding of information and space itself. When matter falls into a black hole, it vanishes from our universe, but quantum mechanics insists that information can never truly be destroyed. So where does it go? The holographic principle offers a startling solution. The information isn't lost, it's smeared across the black hole's event horizon, encoded in tiny, pixel-like bits on its two-dimensional surface. What's truly revolutionary isn't just the answer to the black hole paradox, it's the implication for the entire cosmos. If a black hole's interior can be described entirely by data on its boundary, could the same be true for the universe? Imagine the night sky as a colossal sphere surrounding us, with every star, galaxy, and atom we perceive actually existing as flickering bits of information painted onto that distant surface. The three-dimensional world we move through would then be a kind of illusion, a hologram generated by processes happening at the universe's outermost edge. It's as if reality is a video game, and we're the characters inside it, unaware that everything we experience is rendered from code stored on some cosmic hard drive far beyond our perception. The math behind this idea is eerily precise. In the 1990s, physicist Juan Maldacena discovered a concrete example of holography in action, linking a hypothetical five-dimensional spacetime to a four-dimensional quantum field theory, a duality that showed how gravity in higher dimensions could emerge from quantum interactions on a lower dimensional boundary. Think of it like a shadow puppet show. The complex dance of three-dimensional shapes you see is actually created by flat hands moving against a wall. In the same way, our universe's richness might arise from simpler, flatter physics operating at its edges. Even more astonishing, this isn't just theory. Experiments with ultra-cold quantum fluids have shown behaviors that mirror holographic predictions, as if nature itself is hinting at this deeper layer of reality. But how could this possibly work in practice? One clue lies in the way information scales. In ordinary physics, the amount of data needed to describe a region of space grows with its volume. More space means more stuff to keep track of. But in a holographic universe, the information only scales with the area of its boundary, not the volume inside. Picture a room filled with books. Normally, you'd need to catalog every page to describe the room's contents. But if the universe is holographic, it's as if all those books could be compressed into titles written on the walls with no loss of detail. This bizarre efficiency suggests that the universe might be fundamentally leaner, more optimized than we ever imagined, a cosmic sleight of hand where less truly is more. The implications are staggering. If the holographic principle holds, it could unify quantum mechanics and gravity, two frameworks that have stubbornly resisted reconciliation for a century. Gravity, in this view, wouldn't be a fundamental force but an emergent phenomenon, like the way temperature arises from the motion of particles. Even time might lose its status as a fundamental dimension, becoming just another feature of the hologram. And then there's the existential question. If we're living in a projected reality, what or who is doing the projecting? While the principle doesn't invoke a programmer or deity, it does suggest that our universe's structure is far more malleable, more interdependent than we've ever dared to dream. Yet for all its elegance, the holographic principle remains fiercely debated. Some critics argue that it's a mathematical curiosity with no bearing on the real universe, while others see it as the key to unlocking physics' greatest mysteries. Future experiments, like those probing quantum entanglement or the fine details of cosmic microwave background radiation, might tilt the scales, but whether it's ultimately proven or not, the holographic principle has already reshaped how we think about space, information, and the very nature of existence. It's a reminder that the universe's deepest symmetries aren't always visible sometimes. They're hidden in the pixels of reality itself, waiting for us to decode their secrets. Dark matter is the universe's silent architect, an invisible hand sculpting galaxies into shapes so balanced they defy randomness. Though we can't see it, touch it, or even detect it directly, its gravitational fingerprints are everywhere. In the graceful swirl of spiral galaxies, the perfect spheres of dwarf galaxies, and the vast halo-like cocoons that envelop galactic clusters. These halos aren't just cosmic decoration, they're evidence of dark matter's peculiar preference for order. Unlike ordinary matter, which clumps into stars, planets, and nebulae, dark matter distributes itself with eerie symmetry, forming smooth, diffuse clouds that stretch far beyond a galaxy's luminous edges. It's as if the universe has a hidden rulebook, one where dark matter drafts the blueprint and ordinary matter simply fills in the lines. But how does something we can't see hold galaxies together? Picture a spinning vinyl record. If it were made only of visible matter, stars and gas, it would fly apart from centrifugal force. Dark matter acts like an invisible weight, its gravity providing the extra pull needed to keep everything intact. Computer simulations show that without dark matter's halo, galaxies like the Milky Way would never have formed their iconic disks. Instead, they'd be chaotic blobs, their stars scattered like marbles dropped on a floor. Yet dark matter doesn't just anchor galaxies, it arranges them. In clusters like the Coma supercluster, hundreds of galaxies orbit a shared center of gravity, their paths dictated by the halo's near-perfect spherical distribution. It's a cosmic ballet where the dancers are guided by an unseen choreographer. The real mystery isn't just what dark matter does, it's why it behaves this way. Ordinary matter interacts with light, crashes into itself, and piles up into dense structures. Dark matter, by contrast, seems aloof, passing through itself and everything else like a ghost. This odd indifference is what allows it to form those vast, smooth halos. But here's the puzzle. If dark matter truly ignores everything, why doesn't it just spread evenly across the cosmos? Why does it cluster in halos at all? Some theories suggest dark particles might have a whisper of interaction, just enough to slow them down and let gravity gather them into structures. Others propose that dark matter isn't one thing but many, a family of particles with different behaviors, some sticky, some slippery, working together to sculpt the universe's large-scale architecture. Then there's the elephant in the room. What if dark matter isn't matter at all? A radical alternative suggests gravity itself might work differently on galactic scales, eliminating the need for invisible particles entirely. Modified Newtonian dynamics, or MUND, argues that our equations for gravity are incomplete, and what we attribute to dark matter is really just gravity behaving in ways we don't yet understand. Yet even MUND struggles to explain all the evidence, like the Bullet Cluster, two galaxy clusters that collided, leaving their dark matter halos detected via gravitational lensing, visibly separated from the ordinary matter. It's as if the universe is teasing us, offering clues that point in conflicting directions. The stakes couldn't be higher. Unraveling dark matter's secrets wouldn't just solve a cosmic whodunit, it could rewrite the rules of physics. If dark matter particles are ever detected, they might reveal new forces or dimensions. If gravity is the culprit, we'd need a new theory to replace Einstein's relativity. Either way, the answer lies in those symmetrical halos, their quiet perfection hinting at laws we've yet to imagine. For now, they remain one of the universe's most tantalizing paradoxes, structures so precise, so elegant, yet built by something we can't even see. And perhaps that's the most poetic symmetry of all, the way the cosmos balances what it shows us with what it keeps hidden. The cosmic microwave background should be the very definition of randomness, a relic of the Big Bang's afterglow, its temperature variations scattered across the sky like static on an old TV. Yet when scientists mapped these fluctuations with precision, they stumbled upon something unsettling. The variations weren't entirely chaotic. Instead, they seemed to align along a mysterious corridor stretching across the cosmos, a pattern so improbable that astronomers dubbed it the axis of evil. This wasn't just a quirky name, it was a direct challenge to one of cosmology's bedrock principles, the idea that the universe on large scales should look the same in every direction. What makes this axis so unnerving is its scale. The alignment spans billions of light years, connecting regions of space that should have never been in contact. According to standard cosmology, the early universe expanded faster than light could travel, meaning distant areas couldn't communicate to coordinate their temperature. Yet the axis of evil suggests a synchronization defying this logic, as if some invisible hand tuned the cosmos like a violin string. Some researchers argue it's just a statistical fluke, a cosmic coincidence in the noise. But the odds of such a pattern arising by chance are staggeringly low, roughly 1 in 10,000. That's like rolling 100 dice and getting all sixes. Twice, the implications ripple far beyond a single anomaly. If the axis is real, it could mean our universe isn't as isotropic as we thought. Perhaps it has a preferred direction, a cosmic north, where physics behaves slightly differently. Some theorists speculate this might trace back to the Big Bang itself, a primordial asymmetry frozen into spacetime like a fingerprint. Others propose even wilder ideas, that the axis is a bruise from a collision with another universe during inflation, or evidence of a spacetime vortex twisting the fabric of reality on unimaginable scales. Then there's the unsettling possibility that we're seeing the shadow of something beyond our universe, a structure so vast, it bends the CMB like light passing through a lens. Yet for all the speculation, the axis of evil refuses to surrender its secrets. The Planck satellite's ultra-precise measurements only deepen the mystery, confirming the alignment but offering no clear explanation. Critics point out that human brains are wired to find patterns, even where none exist, a phenomenon called pareidolia, like seeing faces in clouds. But the axis persists across independent datasets, defying dismissal as mere illusion. It's as if the universe is teasing us, dangling a clue to a puzzle we don't yet have the tools to solve. What's most fascinating isn't just the anomaly itself, but what it reveals about our place in the cosmos. For centuries, we've clung to the idea that we occupy no special location, the Copernican principle's insistence that Earth isn't the center of everything. The axis of evil quietly undermines this humility. If the universe has a preferred direction, does that mean we're aligned with it by chance, or is there something fundamentally off about our perspective? Either answer would rewrite cosmology's rulebook. Until then, the axis remains a riddle written in the oldest light we can see, a whisper from the dawn of time that we're only beginning to hear. Our solar system has always been the benchmark for planetary arrangements, a chaotic menagerie of rocky worlds, gas giants, and icy dwarfs, each with wildly different sizes and orbits. But when astronomers began discovering exoplanets in distant star systems, they stumbled upon something unexpected, planetary families that look nothing like ours. Instead of a haphazard mix, these systems showcase rows of near-identical worlds, spaced with the precision of a cosmic abacus. Dubbed peas in a pod, these exoplanets often share startlingly similar sizes and masses, their orbits strung along their star-like beads on a necklace. It's as if the universe took a cookie cutter and stamped out planet after planet, leaving behind a symmetry so exact, it challenges everything we thought we knew about how planetary systems form. The secret to this uniformity might lie in the earliest moments of a star's life, within the swirling chaos of its protoplanetary disk. These disks, vast rings of gas and dust that encircle newborn stars, are the raw material for planets. In our solar system, the disk's composition must have been patchy, with dense clumps forming Mercury's iron core, while sparse regions sculpted Neptune's gaseous bulk. But in peas-in-a-pod systems, the disk might have been far more uniform. Its material spread smoothly like flour on a countertop. As gravity began pulling particles together, planets would have coalesced at regular intervals, each scooping up nearly identical amounts of material from their well-mixed surroundings. But smooth disks alone don't explain the spacing. Here's where orbital resonances come into play, those same gravitational rhythms that sink Jupiter's moons. In these exoplanet systems, young planets likely migrated inward as they formed, their gravitational nudges locking them into harmonious orbits. Picture a group of dancers holding hands, adjusting their steps until everyone moves in perfect time. The result, a chain of planets spaced at predictable distances, their sizes and orbits fine-tuned by the disk's physics. The TRAPPIST-1 system is a textbook example. 7 Earth-sized worlds orbiting so close to their dim star, their years are measured in days. Yet despite their tight quarters, their orbits hum along in near-perfect resonance, a gravitational symphony that's kept them stable for billions of years. This discovery isn't just reshaping planetary science, it's rewriting the story of our own cosmic backyard. For decades, we assumed all solar systems followed a messy, improvisational blueprint. Now it seems our home might be the outlier, its diversity the exception rather than the rule. That raises a tantalizing question. If peas-in-a-pod systems are the norm, what special twist of fate made our solar system so eccentrically varied? Some theories point to Jupiter's early rampage through the inner disk, scattering material and disrupting potential symmetry. Others suggest our Sun's birth cluster was unusually turbulent, its disk peppered with dense pockets that birthed mismatched planets. Yet the most profound implication isn't about the past, it's about the future. If orderly systems are common, then so too might be Earth-like worlds, their similar sizes and stable orbits creating ideal conditions for life. Imagine an entire family of planets, each with comparable gravity, atmospheres, and perhaps even biospheres, all circling the same star. It's a vision of cosmic harmony that borders on poetry, a universe where planets don't just form, but form together, bound by the same invisible rhythms that shape the cosmos. And every time we find another peas-in-a-pod system, we're reminded that the universe's order isn't just written in the stars, it's etched into the very worlds that orbit them. Hidden behind the Milky Way's thick veil of dust and stars, something massive is pulling us and thousands of other galaxies toward it at over 1 million miles per hour. This cosmic enigma, known as the Great Attractor, isn't just a random sinkhole of gravity. It's a gravitational maestro, orchestrating the motion of entire galaxies into a vast, symmetrical flow, as if the universe itself were breathing in unison. What's baffling isn't just the scale of this pull, but its eerie coordination. Galaxies scattered across hundreds of millions of light years move together like leaves caught in a gentle current, their paths aligned with a precision that defies randomness. Normally, such motion would suggest a single colossal mass, a supercluster of galaxies or a black hole of unimaginable size. Yet when astronomers tally the visible matter in the Great Attractor's vicinity, there's simply not enough stuff to explain its grip. This discrepancy hints at something deeper, a hidden architecture of dark matter woven into the cosmos on scales we're only beginning to map. Here's where the symmetry becomes even more intriguing. The Great Attractor isn't acting alone. It's part of an even larger structure called Laniakea, a supercluster of galaxies spanning 500 million light-years. Within Laniakea, every galaxy, every star, every speck of dust flows toward a shared center of gravity, tracing graceful filaments that resemble the branches of a cosmic tree. These filaments aren't chaotic, they're highways of order, shaped by the interplay of dark matter's pull and the universe's expansion. It's as if gravity itself has a preference for elegance, sculpting chaos into harmony. But the mystery doesn't end there. Recent observations reveal that the Great Attractor is just one player in a far grander tug of war. Beyond Laniakea, an even more massive structure called the Shapley supercluster exerts its own gravitational pull, creating a counterflow in the cosmic dance. Between these two titans, galaxies are stretched like taffy, their motions balancing the competing forces with near mathematical precision. The result: a vast dynamic equilibrium where symmetry emerges not from stillness, but from the tension between opposing giants. What does this tell us about the universe? For one, it suggests that what we call chaos might just be order operating on scales too vast for our minds to grasp. The Great Attractor's influence and the symmetrical flow it creates could be a fractal echo of the same forces that shape spinning galaxies or orbiting planets. From the quantum foam to the cosmic web, the universe seems obsessed with finding balance, even in its most violent motions. And then there's the humbling thought that we're caught in this flow, hurtling toward the unknown alongside billions of other galaxies. The Milky Way, for all its majesty, is just one leaf in the cosmic stream, riding currents we've only just begun to measure. Every new map of this hidden architecture peels back another layer of the universe's grand design, reminding us that even in the darkest corners of space, symmetry whispers its secrets to those willing to listen. Quantum entanglement is the universe's ultimate magic trick, a phenomenon so baffling, even Einstein struggled to accept it. Picture two particles born from the same quantum event, separated by billions of light years. Measure one, and its twin instantly snaps into a mirrored state, as if space and time between them don't exist. Einstein famously dismissed this as spooky action at a distance, a phrase that captures both the mystery and his discomfort. Yet decades of experiments have proven entanglement isn't just real, it's a fundamental feature of reality, one that hints at a cosmos far more interconnected than we ever imagined. The heart of this mystery lies in what physicists call non-locality. In our everyday world, influence travels at a leisurely pace. Light takes 8 minutes to reach us from the sun, and a shout across a canyon arrives with a delay. But entangled particles defy this logic. Their connection is instantaneous, transcending distance so completely, it's as if the universe cheats its own rules. Imagine flipping a coin in Tokyo and knowing, without any signal or delay, that another coin in New York must land the same way. That's the eerie symmetry of entanglement, a cosmic choreography that plays out faster than light itself. How does this work? At the quantum level, particles don't exist in fixed states until measured. Instead, they hover in a haze of probabilities, a superposition of all possible outcomes. When entangled particles are created, say, by splitting a photon into two, they share a single quantum description, a mathematical bond that persists no matter how far apart they drift. Measure one, and the superposition collapses, forcing its partner into a corresponding state. It's not communication in the traditional sense. There's no signal zipping between them. Rather, the particles seem to exist in a shared reality where separation is an illusion. This raises a tantalizing question. Could entanglement be more than a quantum quirk? Some theorists propose it's a hidden symmetry woven into spacetime itself, a kind of cosmic glue that binds the universe at its most fundamental level. Think of spacetime not as a static stage but as a living tapestry, with threads of entanglement stitching together regions that appear distant to our limited perception. Black holes might amplify this idea. Their event horizons could act as quantum mirrors, entangling particles inside with radiation outside in a process called Hawking radiation. Even the fabric of empty space might buzz with entanglement, a seething network of connections we're only beginning to map. Experiments are pushing these ideas from speculation to science. In 2017, Chinese scientists used the Misha satellite to entangle photons over 1,200 kilometers, proving this spooky action works across continental scales. Meanwhile, lab setups like quantum erasers toy with causality itself, showing that measurements made after particles are detected can retroactively alter their behavior. It's as if time, like space, is just another variable entanglement ignores. Yet the deepest implications might be philosophical. If entanglement links particles across vast distances, could it hint at a universe where separateness is an illusion? Ancient spiritual traditions speak of cosmic oneness, a unity underlying all things. Quantum mechanics, in its own mathematical language, echoes this intuition. We're left with a humbling thought. The symmetries we see in galaxies, nebulae, and even atomic bonds might all be surface ripples of a deeper, entangled reality, one where every particle, every star, every conscious observer is part of a vast, whispering web. And every time we measure a photon or probe a black hole, we're tugging gently on that web, feeling the universe tug back. The shape of the universe isn't just an abstract curiosity, it's a cosmic fingerprint, a clue to how everything from galaxies to quantum particles fits together in the grand scheme. Think of it like this: if you could step outside the cosmos and gaze back, would it curve inward like a sphere, bow outward like a saddle, or lie perfectly flat like an infinite sheet of paper? The answer hinges on a delicate balance between the universe's density and its expansion, a tug of war between gravity's pull and dark energy's push. Right now, the best measurements from satellites like Planck suggest the universe is flat to an astonishing precision, with a margin of error less than 1%. But flatness here doesn't mean boring. It's a razor's edge equilibrium where the cosmos's total energy density aligns perfectly with the critical threshold needed to avoid curvature. How do we even begin to measure such a thing? The cosmic microwave background, that ancient afterglow of the Big Bang, holds the key. Tiny temperature fluctuations in this radiation act like a cosmic ruler, revealing how space itself bends or stretches on the largest scales. If the universe were positively curved like a sphere, parallel beams of light would eventually converge, like lines of longitude meeting at the poles. A saddle-shaped, negatively curved cosmos would do the opposite, sending light rays diverging eternally. But the CMB's patterns match neither. They align with flatness, a geometry where parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. It's as if the universe balanced its books with cosmic perfection, leaving no room for accidental curvature. Yet the implications of flatness are mind-bending. A flat universe is likely infinite, stretching endlessly in all directions with no boundary, no edge, no outside. That means every possible configuration of matter, every variation of you reading these words in a slightly different reality, could exist somewhere out there, repeated across the void. But here's the twist: flatness doesn't necessarily mean infinite. The universe could also be finite but unbounded, like a video game world where stepping off one edge teleports you to the opposite side. This shape, called a torus, would still obey flat geometry locally while looping back on itself in higher dimensions. Imagine blowing up a balloon, drawing parallel lines on it, then deflating it into a flat sheet. The lines stay parallel, but the topology remembers its hidden folds. The stakes couldn't be higher. If the universe is truly flat and infinite, it challenges our understanding of dark energy's role in cosmic expansion. A spherical cosmos would eventually collapse in a big crunch, while a saddle-shaped one would rip itself apart. Flatness sits on the knife's edge, poised between these fates but still vulnerable to dark energy's accelerating push. Some theorists even speculate that flatness hints at a multiverse, where our universe is just one bubble in a froth of infinite possibilities, each with its own geometry. Others see it as evidence of cosmic inflation, that explosive early growth spurt that ironed out primordial wrinkles into near-perfect flatness. The mystery deepens when we consider anomalies. Why does the universe's measured density align so precisely with the critical value needed for flatness? Coincidence seems unlikely. It's like tossing a coin and having it land on its edge every time for billions of years. This flatness problem suggests something deeper at work, perhaps a self-correcting mechanism or a hidden symmetry we've yet to uncover. Until we solve it, the shape of the universe remains both an answer and a question, a reminder that even in the vastness of space, perfection is never accidental, and every line, every angle tells a story we're still learning to read. Neutron stars are cosmic extremes, crushed remnants of dead stars so dense, a single teaspoon of their material would weigh billions of tons on Earth. Yet even in this realm of unimaginable pressure, symmetry finds a way to assert itself. When these stellar corpses experience starquakes, violent fractures in their crystalline crusts, the energy doesn't explode outward chaotically. Instead, it ripples across the surface in near-perfect geometric patterns, detected by telescopes as precise X-ray bursts. It's as if the universe took a sledgehammer to a diamond and watched it shatter into mathematically perfect fragments. What makes these symmetrical starquakes so astonishing is the environment they emerge from. A neutron star's crust is a lattice of atomic nuclei packed so tightly, they form a rigid, crystalline shell floating atop an ocean of superfluid neutrons. When stress builds, whether from the star's ludicrous spin, some rotate hundreds of times per second, or abrupt adjustments in its magnetic field, the crust cracks like glacial ice, releasing pent-up energy. But here's the twist: the superfluid beneath acts like a cosmic shock absorber, damping chaotic vibrations and filtering the energy release into clean, harmonic oscillations. Picture dropping a pebble into a pond of liquid helium. The ripples would be unnervingly smooth, their symmetry preserved by the fluid's frictionless flow. On a neutron star, that same principle scales up to seismic proportions. The resulting X-ray patterns are anything but random. Some starquakes produce oscillations that resemble the vibrational modes of a bell, ringing at specific frequencies dictated by the star's density and magnetic field. Others send energy pulsing outward in concentric circles, like a stone skipping across a superfluid lake. The most mesmerizing are the torsional oscillations, where sections of the crust twist against each other in precise mirror image motions, as if the star were executing a pirouette in slow motion. These patterns are so consistent, astronomers can use them to probe the star's internal structure, much like geologists decipher Earth's core by studying earthquake waves. But the real mystery lies deeper. Why does such symmetry persist in conditions that should breed chaos? The answer might lie in quantum physics. At neutron star densities, matter behaves less like familiar solids and more like a quantum liquid crystal, where particles align in orderly patterns even under extreme stress. Protons in the core may pair up into superconducting fluids, while neutrons form Cooper pairs akin to those in superfluids on Earth, sliding past each other without friction. This quantum orchestration could channel the violence of a starquake into predictable, symmetrical releases nature's way of imposing order at the edge of collapse. The implications stretch far beyond neutron stars. If matter can self-organize into symmetrical patterns under such extremes, it might reshape how we think about other high-energy phenomena, from magnetar flares to the quark-gluon plasma of the early universe. Even gravitational waves, ripples in space-time itself, could carry faint echoes of these quantum symmetries, detectable by future observatories. Every starquake is a message in a bottle, tossed from the edge of physics as we know it, reminding us that even in the most ferocious corners of the cosmos, harmony finds a way. What if our universe isn't the only one? Imagine a cosmic hall of mirrors where every reflection isn't just an image, it's an entirely separate reality, each with its own unique twist on physics. This is the Multiverse Hypothesis, a mind-bending idea that suggests our universe might be one thread in an infinite tapestry of parallel worlds. Some of these universes could mirror ours almost exactly, with stars, planets, and even versions of ourselves living nearly identical lives. Others might be unrecognizable, where gravity pushes instead of pulls, light travels backward, or time itself flows in reverse. And here's the kicker, these alternate realities wouldn't just be random, they could be bound together by symmetries so profound, they make the patterns we see in our own cosmos look like child's play. Take the concept of mirror matter, a hypothetical substance that would behave like ordinary atoms but with flipped properties right-handed instead of left-handed, or with opposite electric charges. If such matter exists, it might form entire mirror stars and planets, invisible to us except through gravity's faint tug. Even stranger are theories like brain cosmology, where our universe is a three-dimensional brain floating in a higher dimensional space with other brains hovering just out of reach. Collisions between these brains could explain cosmic events like the Big Bang, not as a singular beginning, but as one note in an endless symphony of collisions and rebirths. The implications ripple through every corner of physics. If the multiverse is real, the fine-tuning of our universe's constants, the precise strength of gravity, the exact mass of an electron might not be a miracle, but a statistical inevitability. In an infinite sea of universes, every possible combination of laws would arise somewhere, and we just happen to inhabit one where conditions allow for galaxies, life, and consciousness. It's like walking into a library containing every book ever written. Of course, you'd find one in your language. This anthropic principle offers a humbling perspective. Our universe's apparent perfection might not be special, just survivable. Yet the multiverse isn't just a cosmic cop-out. It could explain anomalies in quantum mechanics, like why particles behave differently when observed. Some interpretations suggest that every quantum decision spawns new universes, meaning the famous Schrödinger's cat isn't just alive or dead in our world, but both, with each outcome playing out in a separate branch of reality. These branching timelines would weave a fractal tree of possibilities, its symmetry hidden in the math of wave functions. Of course, critics argue that the multiverse is untestable, more philosophy than science. But recent advances hint at ways to peek beyond the curtain. The cosmic microwave background might bear scars from ancient collisions with other universes, like bruises on an apple. Gravitational wave detectors could one day catch echoes of these crashes, whispers from beyond our spacetime. And if mirror matter exists, it might leave traces in particle colliders, ghostly particles that vanish inexplicably, as if slipping into another dimension. Whether the multiverse is real or not, the idea reshapes how we see symmetry. No longer just a feature of our universe, it could be the glue binding all realities together, a hidden language spoken across existence. Every spiral galaxy, every quantum entanglement, every law of physics might be one variation in an endless chorus, And if that's true, then the symmetries we've spent this video admiring aren't just beautiful accidents. They're clues, hints that we're part of something far grander, a cosmic pattern repeating itself in ways we're only beginning to imagine.